therefore a very, very serious incompatibility which should be avoided. Therefore, we are saying we should not add together disappearing. That is the incompatibility in vitro outside. So one should not mix an aminoglycoside and a beta-lactam in the same syringe. We are now looking at streptomycin because we remember we also have an interest of, we are still on the antimicrobial agent, and streptomycin is one of them. And when we look at the aminoglycosides, we have already looked at, I think with the exception of spectinomycin, and of course, with the exception of spectinomycin, this is a general structure whereby we are saying you have this as our amino cyclito. Of course, it will also be different for streptomycin, because streptomycin, this will not be an amino group. This will be an guanidino moiety. That will also be a guanidino moiety. It will also be, that is for streptomycin. It will also be for spectinomycin. For spectinomycin, this will be this will be a methyl amino group, and that will be a methyl amino group. For those two drugs, of course, that group is different. For the majority of the aminoglycosides, that is the expected general structure, where at that position you will have an amino sugar, and also at that position you will have an amino sugar. So I can see that structure went a little bit low. So let me check what was supposed to be. So we are looking at the characteristics, and we can note, I'm just trying to read this from what this was erased a bit. According to the physical properties, aminoglycosides And aminoglycoside antibiotics are powders of white, so according to the physical aminoglycosides are powders of either white, yellow, or cream colors. So most of them are powders. They will have white, yellow, or cream colors. They are hygroscopic, or should be hygroscopic. In other words, they pull water, freely soluble in water, and practically insoluble in low solubility in most organic solvents. And they are optically active. They have sugars, and sugars are optically active. So they can normally formulate them into powders, and because of their they must be well stored, of course, without being exposed to the air, because they can pull in water. Once they pull in water, of course, they can undergo degradation. So therefore, they must be well stored. The aminoglycoside structure activity relationship, all the aminoglycosides are very similar pharmacologic, pharmacodynamic, and toxic properties, but only streptomycin, STM is standing for streptomycin, and to a lesser extent, kanamycin are used for management of TB. So they have the same similar pharmacologic, pharmacodynamic, and toxic properties. Only streptomycin and to a lesser extent, kanamycin are used for treatment of TB. This is an indication for the narrow band of structurally allowed modification giving rise to active analogs. Indeed, when we look at those drugs, we have seen minimal structural changes, and the only structural change that we have actually seen is at position number one, where the others are naturally occurring, and they occur that way. You don't change them; they are supposed to remain the same. Modifications. So now we are looking at streptomycin. Kindly look at your structure of streptomycin. If you look at your structure of streptomycin, I do believe I have it. Look at your structure of streptomycin, because the streptomycin is the main one which is used in treatment of TB. And remember, we are studying the aminoglycosides, but of course our other interest is the antimicrobacterial drug. So we need to discuss streptomycin as an antimicrobacterial agent. So when you look at streptomycin, of course, we didn't mention even the arrangement of the rings differ. Even the arrangements of the rings differ. So if you look at this, ring 1 is not the aminoglycoside, and I'm sorry, the amino sugar. Ring 1 in streptomycin is actually the amino inositol, streptidine. So you start that as our ring 1, and then ring 2, as you can see, is actually the ribose sugar. It is also not an amino sugar, it is a ribose sugar. Look at this, it is a ribose sugar, and streptomycin has only one amino sugar. So streptomycin has only one amino sugar, which we call N-methyl L-glucosamine. So that is the only N-methyl L-glucosamine is the only amino sugar that is found in streptomycin. And as we can see, the composition of the rings, or the composition differs, and no wonder there is a difference in the spectrum of activity. That's what we say. They normally have similar pharmacological activity, but once you differ, you bring about some structural modification, be it in the arrangement of the rings, be it in the type of rings, then you can see we are able to alter the activity of the drug. So this definitely is streptidine having the guanidino moiety at position number 1 and at position number 3. Then it has a special ribose sugar. If you look at this ribose sugar, you will see at position number 3 prime, our ribose sugar, one of the hydrogens has been replaced by a methanol. The unit has been replaced by a methanol unit. This is C double bond OH methanol group with retention, or an aldehyde group with retention. And at position 4 prime, the hydroxyl group which would be there has been replaced with a methyl group. So that makes this sugar completely different. It has a methyl group at 4 prime. It has an aldehyde group or a methanol group at position number 3, and that ribose sugar is known as L-streptose. That sugar, again, is responsible for quite a number of characteristics that are found in streptomycin, be it chemical characteristics. That sugar has a lot of influence on the properties of streptomycin. So that it was important for us to understand understand the structure of streptomycin, even as we discuss the structure modification that can be done on the same. So we are saying this in addition, so modification of the alpha streptose, so that is the streptose, we have looked at modification of the alpha streptose portion of streptomycin has been extensively studied, and reduction of the aldehyde. We have looked at that aldehyde group at position number 3, aldehyde to the alcohol results in a compound, the dihydrostreptomycin, that has activity similar to streptomycin, but with a greater potential for producing delayed severe deafness. So once you have that drug and it is equipotent, but has much more toxicity, then you have no interest. So we are saying the aldehyde can be reduced to the alcohol with retention of activity, but increase in toxicity and therefore no added advantage. Oxidation of the aldehyde to the carboxyl group or conversion to the Schiff's base. The Schiff's base can either be an oxide, can be a semicarbazone or a phenylhydrazone, results in inactive analog. So we are saying the carboxyl group, the aldehyde is important both for effective or for safe or for minimal toxicity, and also it is necessary for the activity of these drugs. You cannot oxidize it to the carboxylic group. You cannot oxidize it to the various, the oxime, the semicarbazone, or the phenylhydrazone, that will in loss of activity. And these are the ones we are talking about. This is the structure. The first one is the semicarbazone. This is a semicarbazone. That is the structure of a semicarbazone. That is the structure of the oxime. That is the structure of the phenylhydrazone. So we are saying we cannot convert it to a semicarbazone. We cannot convert the aldehyde into a phenylhydrazone. We cannot convert it to an oxime. If we do any of these structural modifications, then the resultant molecule will be inactive. So therefore, we are saying indeed the best group at that position is the aldehyde. At the position number 3 of streptose, the best group at that position of the aldehyde is the aldehyde, gives you best potency and also gives you least. Oxidation of the methyl group in the alpha streptose to a methylene hydroxyl group gives an active analog that has no advantage over streptomycin. Again, remember at position 4 we have a methyl group. We are saying we can oxidize it to a methylene or methyl alcohol, methyl hydroxyl group. Again, the resultant molecule has no added advantage over streptomycin, so that again is not necessary. Modification of the aminomethyl group in the glucosamine portion of the molecule by demethylation or by replacement with the larger alkyl groups again reduces activity. Aminomethyl group, remember you said it is N-aminomethyl or N-aminomethyl glucosamine. We are only saying that aminomethyl group cannot undergo demethylation, or you cannot replace the methyl group with a larger group like ethyl group or propyl group. Again, that will reduce activity. Again, what we are emphasizing, streptomycin, which is of course the drug which is found in the market, has the best structure for optimum activity. All those groups that are in the specific positions are there with a reason. You cannot change those groups. If you change those groups, then the resultant molecule that will be formed will have lower activity than streptomycin, will have higher toxicity than streptomycin. So why bother? Removal or modification of either the guanidine in the streptidine decreases activity. So what we are saying is that there is no acceptable. In other words, we are saying for streptomycin, there is no acceptable structure. It is the best molecule which has been so far discovered for management of TB. Metabolism. And do remember, we are saying that most of these drugs have many hydroxyl groups, have many amino groups, so most of them will be water soluble. They will be excreted as they are. More often than not, they will be excreted as they are and change in urine. And this can be explained by their very high water solubility. Metabolism appears to be insignificant on a large scale, but it is implicated as a major mechanism of resistance. So the mechanism, when these drugs are metabolized, indeed the metabolism of these drugs is their deactivation, because metabolism through acetylation, phosphorylation, that indeed results in their acquiring, or the microorganisms acquiring resistance against these drugs. One problem with streptomycin is the development of resistant strain of Mycobacterial tuberculosis. And that's why, again, we normally will give it in combination. You do not give these drugs on their own. They will be given in combination to try and prevent resistance, but ultimately it still develops. Combination drug therapy was partially successful in reducing this problem, but over time, resistance has greatly reduced the value of streptomycin as a chemotherapeutic agent for treatment of TB. Again, remember the dangers of multi-drug resistant TB. Various mechanisms may lead to resistance in Mycobacterial tuberculosis, and we have already mentioned those methods of resistance is mainly through deactivation. So there can be permeability barriers, results in the streptomycin not being transported through the cytoplasmic membrane, but so there is permeability barriers. In other words, microorganism encodes for enzymes such that it reduces its permeability towards the drug. And remember, for all antibacterial agents, you must reach the minimum inhibitory concentration within the microorganism. So if it does not allow for the drug to permeate, or drug to diffuse, or drug to move it in, even through active transport, then of course you will have a challenge. Then, and of course also there is the inactivation, which we have already mentioned. The enzyme responsible for inactivation, we've already mentioned transferase and the phosphotransferases. Those are the main one, adenyl transferase and the phosphotransferases. The adenyl transferase catalyzes adenylation of carbon 3 hydroxyl group in the N-methyl glucosamine moiety. So the N-methyl glucosamine, you have a carbon 3 hydroxyl group. It will, remember, the adenyl transferase works on hydroxyl groups in the N-methyl glucosamine moiety to give the O3 adenylated metabolite. So the adenyl transferase, or the APH will not APH ANT will work on the carbon 3 hydroxyl group, while the phosphotransferase will phosphorate the same carbon 3 hydroxyl group to give the O3 phosphorylate metabolite. So the same group can also be phosphorylated, and we are saying to give the O3 phosphorate metabolite, phosphorylation appears to be the most significant clinically. So we do not have acetylation. What we have is carbon 3 hydroxyl group in the glucose N-methyl glucosamine sugar undergoing either a phosphorylation or adenylation, and phosphorylation is the one which is most significant. The result of this chemical modification is that the metabolites produced will not bind the ribosome. So this is protection, or actually deactivation, as we have already said. We are not protecting the ribosome, we are deactivating. We are blocking the site, the pharmacophoric site within the drug, and the drug therefore cannot bind the receptor, and of course that will result in the established development of resistance by the microorganisms. That, of course, we have already mentioned. So we are saying, if you look at this, of course, we are saying that is our 1 prime. That is our 1. So this is our 1 prime on the ribose sugar. So we are talking about this N-methyl L-glucosamine. We are talking about the 3 prime position. So that is our 3 prime position, and we are saying this hydroxyl group can either undergo phosphorylation or it can undergo. So this, you see, in the other rings, this was number 1. This is what we are looking at, number 1, and we still had the 3 prime. And still had this 3 prime when you had a hydroxyl group, but incidentally for the N-methyl glucosamine, looks like the 4 prime is not a problem. 4 prime is not a problem. The count is a 3 prime, which can undergo either adenylation or phosphorylation, resulting in deactivation of the streptomycin. I don't know why. course, as we have already said, it is naturally occurring, and of course, and it has some use against, of course, Mycobacteria tuberculosis. We've already mentioned that there is indeed a lot of resistance, but of course, it can be used for the sensitive. The microorganisms are sensitive. One has to do culture sensitivity to find out whether the microorganisms are sensitive, and it can work if the microorganisms are sensitive. We have also said kanamycin and amikacin can also be used for the same management of TB, but amikacin is much, much more expensive. Remember, it is the semi-synthetic derivative of kanamycin A. Characteristics, we've already mentioned, it's hygroscopic, very soluble in water. We mentioned all that. Of importance to note is that it is basic in nature. It has a basic property. It is basic in nature. Of course, most of the aminoglycosides will be basic in nature because they have amino groups. So basic in nature due to the presence of the nitrogen-containing groups, the two guanidines and one N-methyl amino group in the N-methyl glucosamine, and readily forms acidic salt. So we will find that the streptomycin is formulated as streptomycin sulfate. It is formulated as streptomycin sulfate. In a weak acidic medium, streptomycin is stable, but in strong acidic and especially in basic media. So it is stable in weak acidic media, but in both strong acidic media and especially in basic media, it hydrolyzes into its various components. So it will hydrolyze in streptidine, of course, this is amino inositol, and then streptobiosamine. Streptobiosamine is a combination of the N-methyl glucosamine and the streptose, and further subjected to basic media, it will cleave and it will give you the three components. So in basic media, hydrolyzes into streptidine and streptobiosamine, which decomposes further to N-methyl L-glucosamine and L-streptose. So we are saying the streptomycin is not stable in basic media, not stable in basic media, and we will be able to find out, to see that instability in basic media has been utilized for its assay and identification. Next, I said we are discussing more of the streptomycin because the streptomycin is the one which is used mainly for management of TB, and we want to discuss antimicrobacterial agents. So I decided to combine. So once we finish, we'll be done. We're looking at identification, and you can identify through TLC. When you do TLC or thin layer chromatography, you look for the pure compound and you spot them both. And of course, you will compare. It has a name that I would remember. You will compare the distance that the compounds have moved. And once you compare the distance the compounds have moved, you will see that those which are at equivalent distance. And definitely, if you have your standard, which is the streptomycin, and you have your sample, if it has streptomycin, definitely you will have some of the compounds having moved equal distance, and definitely you'll be able to identify your streptomycin. So thin layer chromatography. We also do have what we call the Malto test. And when we talk about Malto test is because we did mention, first of all, if you subject streptomycin into strong basic media, it will be hydrolyzed into the three components, streptidine, of course, streptose, and N-methyl glucosamine. Then if you continue and you subject your streptose to further basic media plus temperature, then it will be converted to what we call malto. So this is streptose. You can remember streptose has an aldehyde at position number 3. Of course, it has a methyl group at position number 4. So therefore, we are saying when you subject streptose to a basic media plus temperature, it has changed into malto, and that change occurs through dehydration and isomerization. So if it is changed to malto, then this malto, if you add ferric ammonium sulfate in acidic media, the malto will form a complex. So you can see you can see this is a double bond oxygen. This is a dative bond. Remember, you do have, that's a dative bond. And this is an oxygen OH that goes ionization. So this is an ionic bond, this being O minus, and you have that Fe3 plus. So all we are saying is that this can happen when you add ferric ammonium sulfate in acidic media to maltol. You will form this complex, and that complex has a specific color, and I think it is usually violet in color. And therefore, if you add sodium hydroxide, ferric ammonium sulfate to a sample, if it contains streptomycin, then you will see a violet color, or a violet product will be formed. The solution should change to a violet color, or it should give a violet compound. And once you see that, then you know that there is streptomycin, or streptomycin is part of that mixture. So remember, you're just doing identification. How can you identify streptomycin? You can do so using the maltol test, and the maltol test is where on the streptomycin you add sodium hydroxide and a bit of temperature, and you will get the maltol. The maltol is also known as alpha methyl beta oxy gamma pyrone. This should be PY, pyrone, not an I, pyrone. And some, of course, put an E, but I don't think that matters. And if you look at that, is the oxygen. So this is the alpha, and that is the beta, and it's gamma pyrone because of the positioning of the oxo group, or the carbonyl group. So that is maltol, alpha methyl beta oxy gamma pyrone is a maltol. That maltol, we are saying, is the one which undergoes chelation. It undergoes chelation with ferric ammonium sulfate. Ferric ammonium sulfate is just giving you the ferric ions, and of course the maltol, we undergo complex formation with the ferric ions to give us that complex. And that complex, we are saying, it can be extended. You can have, so it can form, I think it can join ferric 3 plus. I think it can join another one. Yes, you can have 3 of them. You can join another one here, you can join another one there. So that is what these 3 stands for. You can have 1, another 2, another 3. So the ferric ion can be able to chelate 3 molecules of maltol, forming a very a stable complex, and that stable complex is colored. So therefore, change of color, violet color, indicates that streptomycin is available. So that's one way of streptomycin maltol test. Another way of identifying streptomycin is what we call the Sakaguchi reaction. Sakaguchi reaction. And when we talk about the Sakaguchi reactions, here we are looking at the guanidino moieties. Streptomycin has guanidino moiety. So even if you have another compound which has a guanidino moiety, then it will also be identified. So this is not very specific for streptomycin, but it is specific for any compound that has guanidino moieties. So the Sakaguchi reaction on the remnants of the guanidines, there is a formation of a violet-red color with appearance in a basic medium under the action of alpha naphthol. You know, you can have 1 naphthol, you can have 2 naphthol. Alpha naphthol is where the hydroxyl group is at position number 1. So you can have your alpha naphthol. That was that. So you have your alpha naphthol, and the alpha naphthol is the hydroxyl group is at position number 1, and you add sodium hypobromite. Sodium hypobromite is with this bromine and oxygen. So you have the Sakaguchi reaction, you have the guanidino moiety, and as I've said, it's not specific for streptomycin, but it is specific for any drug or any compound that has the guanidino moiety, and there will be formation of a violet-red color in basic medium. So this time using for just like we were doing first, use basic medium, but the red color in maltol test is formed in acidic media. So this one remains basic medium under the action of alpha naphtho and concentrated sodium hypobromite. So after acidic hydrolysis, the substance does not give the reaction with alpha naphtho and concentrated sodium hypobromite in basic solution. It remains yellow in color. So we are saying you cannot do this test in acidic media. You can only do it in basic media. When you do it in basic media, you will get your violet red compound or complex. And that again, it will tell you. If you are sure, of course, it was an aminoglycoside, then you know the aminoglycoside is actually streptomycin. Compounds with the guanidine moiety give the color with reagent sodium hypobromite. And that's why I've said, because it is not specific for streptomycin, but it's specific for the guanidino moiety. So if you are told you have you have mixtures of aminoglycosides, identify perhaps in which mixture there is a presence of streptomycin, then this test will be able to identify for you that you have streptomycin, because streptomycin has the guanidino moiety. So you can see the change is that, of course, here is our alpha naphtho. We start alpha naphtho has a hydroxyl group there. So from the sodium hypobromite, you have addition of bromine and you have a addition of hydroxyl group. And then, of course, this group here is a group that has come from our streptomycin. So our streptomycin is continuing this. This is a guanidino moiety, and R is representing the other structure of the streptomycin. So you can see, of course, it will be R, NH, C, double bond N, and there will be an NH2. So that NH2 is the one which is complexing with naphtho in the presence of sodium hypobromite, because you can see there is a change in the naphtho itself. There is addition of a bromine, there is addition of hydroxyl group, and then, of course, there is the addition of the amino group, of the free amino group, to the changed naphtho ring, to the substituted naphtho ring, to get this complex, and that complex is the one which is having a violet red color. That must be done in basic media. If you do it in acidic media, you will say your test is negative. You get a false negative. That is identification. That is, we want to identify whether that drug is present. Now, you can also do us